So hello everyone, my name is Chen Xi, and I'm a PhD student here in UTA in the mathematics department. And today I'm going to talk about matrix governing equations for the incompressible flow. And first, I want to thanks to Dr. Steiner and his research team. Their work gives me a lot of inspirations, although it's in two different fields and it leads to different paths, but at least it shows me the first step, and hopefully it will lead me to my final goal, the Lutex dynamics someday, hopefully. And first, let's just derive this matrix governing equation. And for incompressible flow, this is the Navier-Stokes equation in the tensor notation. Here, partial t is the simplified notation for partial over partial t, and ui, and plus uk partial k of ui. Here, double k means summation. That equals to negative 1 over density rho times partial I of pressure P plus this newest kinetic viscosity times Laplace of ui. And then we can apply another derivative, partial j. So here, partial j stands for partial over partial xj on both sides of the equation. So we have partial j, partial t ui, and so it's the same. And for the first term, the red one, we can just commute partial j and partial t. And for the second one, we have uk here and ui here. We need to apply the product rule. And on the right-hand side, we can basically just put them together. So this is what we have, partial t of partial j ui. And here we are taking derivative first on the second part. So we have uk partial k of partial j ui. And if we compare this and the original equation, we can notice this is the time derivative, and this is the convection term for partial j ui, which means these two terms together is the material derivative of partial j ui. And here is partial k ui, this one, and then partial j of uk, we're taking derivative for the first one. And so this is like the ith row, and k runs from 1 to 3, is the 3 numbers in the ith row. And here is the jth column. It's the 3 numbers on the jth column. When we multiply them separately, add up together, that's what we do when we multiply two matrices together. So this term will end up as a square of a matrix. And here is the second order derivative for pressure P. And this is again new Laplace of partial j ui. So this partial j ui is just the velocity gradient matrix. And we can write it in this way. So here ux, uy, uz, the subscripts denotes the partial derivatives. And we can also denote this pressure matrix P as 1 over rho, and here are all the second order derivatives for the pressure P. And we can write it as in this way. So here this P stands for kind of normalized pressure, which is pressure over density. In incompressible flows, the density is a constant, so we can just kind of normalize it with pressure. So we can thus obtain this matrix governing equation, the material derivative of u, d over dt of u, plus u squared, plus this pressure matrix P minus new Laplace u, that equals to 0. And we can verify it quickly with a solution we already know, which is Taylor-Green vortex. So this is the exact solution I find for Taylor-Green vortex. U equals to e to the negative 2 nu t of negative cosine x sine y, and v equals to e to the negative 2 nu t cosine y sine x. And here is pressure, it equals to negative density rho over 4 e to the negative 4 nu t cosine 2x plus cosine 2y. And we can find the velocity gradient matrix by simply just taking partial derivative on x and on y. So this is what we got. And also we can find the pressure matrix P. So here P over rho, we just divide it here and then just take a derivative. And here it's, this term is only about x, this term is only about y. So when you take partial x, partial y, they just 0. And then we can simplify a little bit. And we can notice that partial u over partial t, which we just bring negative 2 nu in front, it equals to negative 2 nu of u. And here, these are all trigonometrics. You're taking second order derivative, you get negative of what you have. So partial square of partial x of u is negative u, and you have two of them, you add them, it's negative 2u, and there's a nu in front. So these two terms are equal. And here I just put our answer here from the previous page. And we can square it. We got the formula for u square. It's scalar times the identity matrix. And we can also just taking derivatives, multiply it with u and v from the previous page. This is what we got. And simplify it. This is what we got. And then we can add these two terms together. So sine square x, they factor out. Cosine square y, sine square y, that's 1. And here cosine square x factor out, cosine square y, sine square y, that's 1. So basically this is sine square x minus cosine square x, which is negative of this term. And similarly we have for this one, it will be cosine square x minus cosine square y, which is anyways negative for this term. So we got our conclusion that these terms add up together, and also combined with what we have in the previous page, we verify that this function satisfies for the exact solution of the Taylor-Green vertex. So we just verify it quickly here. And here let's talk about how to solve this matrix equation numerically, not exact solution. So first we can reduce one variable by letting wz equals to negative ux minus vy, because we are dealing with incompressible flow. And since the trace of u equals to 0, which means the trace of d over dtu and the new Laplace u, they are both 0. So this two term has 0 trace, thus trace of u squared plus p should be 0. And the trace of the p matrix, which is all the second order derivative on x, on y, and on z, we add them, it is Laplace p. And it equals to negative 2 times ux squared plus vy squared plus ux vy plus uzwx plus uyvx plus vzwy. And you can also simplify it into the square of the magnitude of vorticity minus the Frobenius norm of the matrix U and then square. So, and then we just look at this matrix U. We have 8 variables, so we have 8 equations for time matching. And we just list them here. So the first two is about ux and vy, which is at these two positions. And the second pair I pick is uy and vx. And then we have uz and wx, which is these two. And we also have vz and wy, which is these two. And we can also get the vorticity transport equation if we just subtract these three pairs, because Vx minus Uy, it's omega z, and similar we have here. So if we subtract both of them, and we can get the verticity transport equation. So totally we have 12 variables to solve. 8 of them is the velocity gradient, and we also need to find u, v, and w for time matching, the convection term, and we also need to find the pressure P. So from these 8 time matching equations, we can get the 8 velocity gradients from the previous step to the next time step. And to get u, v, w, and p for the next time step, we need to solve 4 Poisson's equation. So here Laplace p equals to this one, we have seen it before. And here it's Laplace u, Laplace v, and Laplace w. And here, because it's ux taking another derivative on x, it's second order derivative on x. So, and here wz is just a negative ux plus vy. So in theoretical, we can solve it in this way. And now I want to mention about Lutex and resistance. So resistance is something I developed 2 years ago and published last year in this paper. And I've also given a detailed mathematical derivation on Sunday in the short course. So I'm just going to mention the result here instead of another an hour and a half. So here we have 3 different cases depending on the eigenvalue status for the velocity gradient matrix U. So the first one, when the discriminant is positive, we have 1 real and 2 complex conjugate eigenvalues. We call them lambda r, and 2 complex conjugate is lambda cr plus or minus I lambda ci. And second case is when the discriminant is 0. We have repeated eigenvalues. We call them lambda 1 and lambda 2, or just lambda. And for the third case, when the discriminant is less than 0, we have 3 distinct real eigenvalues, and we call them lambda 1, lambda 2, and lambda 3. And the first case is also classified as the rotational points, and the second and the third are classified as the non-rotational points. And let's look at the first case. So in the first case, we can transform this velocity gradient matrix into the principal coordinates through a special orthogonal transformation. And then from there, we can just decompose that into 3 parts, stretching and compression, which is the diagonal. I mark it in red. And the rotation part, it's r over 2, and negative r over 2, the anti-symmetric part, I mark it in green. And the shear term, which is epsilon, c, and eta, the nilpotent part, and I mark it in blue. And to find the magnitude of this r, we need to find the unit eigenvector of this u with respect to the real eigenvalue, lambda r. And we also require that omega dot r has to be positive. And thus, we have this formula to find the Lutex magnitude for R. And we can look at the second case. So from the first case, we're just taking limits, let R approaching to 0. And then we got the second case, so lambda CR became the repeated real eigenvalues, we call it lambda 1. And lambda r became another real eigenvalues. We just call it lambda 2. And for the third case, with 3 distinct real eigenvalues, and this is the principal matrix we designed for the triple decomposition. So on the diagonal, we have lambda 1 plus lambda 2 over 2, lambda 1 plus lambda 2 over 2, and lambda 3 as the stretching or compression term. And we have symmetric L over 2, and I call it the resistance. And we have epsilon, c, and eta, which is the shear part. And notice that if we pick different choice of distinct real eigenvalues, we end up with 3 different resistance. So to calculate this one, first we need the eigenvalue for lambda 3. And again, we require that this is a unit eigenvector, and omega dot r has to be positive. And we also after we calculate the 3 different resistance, we pick the minimum of them. So the reason why we define this resistance is because fluids can have the vorticity or shear, but not having rotation. So we define this symmetric matrix to represent this resistance term. And in my opinion, that's the non-rotational, for the non-rotational point, if it's imposed by a rotation term, which is an anti-symmetric matrix, the resistance will be consumed and it will increase the shear. And once this resistance is depleted, this non-rotational point will be converted into the second case from the third case. And so we will choose the eigenvector on that direction such that the resistance is the weakest as the principal axis r, because on that direction the rotation is most likely to take place, and that is due to the bucket effect. And another thing about Lutx and resistance is negative resistance and the Lutx, they are deeply connected. So suppose we just plug in the 2 complex conjugate eigenvalues as our lambda 1 and lambda 2 into the formula for the third case, which for the non-rotational point. And lambda 1 minus lambda 2 is actually plus or minus I2 lambda ci. We square it, we got negative 4 lambda ci squared. So, and we'll use this is the formula for negative resistance. And we plug in lambda 1 minus lambda 2 squared as negative 4 lambda ci squared. We got the formula for the Lutx magnitude. So this is why I define this resistance as a kind of continuous extension for the Lutx from rotational points to non-rotational points, from a positive number to 0 and then to negative numbers. And of course, in the second case, for the resistance, it's 0, and also for Lutx, that term is 0. So we can use this negative L as a uniform parameter for both rotational and non-rotational points. It is the Lutx for this rotational point, and it will be the negative resistance for non-rotational points. And here is some figure. I put it in the paper. And this is data from our simulation of a flat plate. And so the streamwise direction is the x direction. And these are the sections, YZ sections. So it's x equals to something. And here the red part, so the color stands for this uniform parameter, Lutx or negative resistance. So when this value is positive, it means this point is a rotational point, and this value stands for the Lutx magnitude. And if we have a negative value at this point, it means this point is non-rotational, and this negative value is negative resistance. And positive values are marked in red, negative values are in blue, and we can see we have some vortices here, and we have some resistance in here in the middle. And as x increases, the situation became more and more complicated. It looks more like turbulence. And here I also put dots and cross. It represents the x components of the Lutx vector. So it tells us whether this vertex is like going into the direction or it's going out of the direction, out of the screen. And also we have some even larger x values, and this situation is more turbulence. And actually in our simulation, the z is totally from 0 to 60 something. But here I only kept it at 5 or 7, and here it's just 20, because above that, everything just 0. So I just cut it. So which means the Lutex and resistance, they only kind of appear at the boundary layer. Now let's look at this Lutex and resistance. Oh, okay, let's look at this in 2D cases. So for the principal matrix, we can just write it in this way in 2D. And so the orthogonal transformation preserves the trace and also preserves the magnitude of the verticity. So we can set these equations, which means on the diagonal, the number is just ux plus vy over 2. And this number, epsilon plus r over 2, it's the absolute value of omega minus r over 2. And this number over here, it's the absolute value of verticity minus negative L over 2, which means in both cases, we can use this uniform parameter and write the principal matrix in this way. And then we also know that the determinant is also preserved in orthogonal transformation. So we set up this equation. This is determinant of the original matrix. This is from the principal matrix. And we notice that this is actually a quadratic equation for negative L. So we simplify it, and then we can solve it with the quadratic formula, get it with two solutions. And we know that this negative L, it can be positive for Lutex, it can be negative for negative resistance. So we pick the negative sign here, and that is what we got. So we have a function which related to only 4 numbers on the velocity gradient matrix, and it represents Lutex and also negative resistance. So it's exactly the same function in 2D case. And here is special case I designed. It's another artificial flow, 2 lambda ocean vortex. I put it in negative 1, 0 and 1, 0. And we notice that for Lutex and resistance, this tells us exactly what we have. We have a vortex core here, vertex core here, but the streamline tells a different story. It says we only have 1 vertices and it's centered at the origin, but in reality we have 2 and none of them is centered at the origin. So because this is artificial, adding 2 solutions of the nonlinear PDE doesn't guarantee that's a solution. So we can use this as an initial condition and run the simulation. So this is what we did for the simulation. It's ranging from negative 10 to positive 10 for both x and y. I put 2 vertices at negative d0 and d0. D is 1 or 2 for 2 different cases. And the grid resolution is 128 by 128. And I'm using the numerical formula for derivative with 4th order accuracy, which means we require 2 layers of grid, 2 grid points of a layer on the outside for the boundary condition. And time step is 0.004 per step, and we totally have 10,000 steps. And the time marching way, I'm using the Craig-Nicholson method. And here's the result. And for more details about this simulation, I will talk about tomorrow in my online talk. And that will be more about the algorithm. So let's look at the first one, when d equals to 1. And this is just Lutex without resistance, and the arrows is velocity. And actually, they are the same length, but the color stands for the magnitude of the velocity. So So we can see how these two vortices just rotate and combine together. And there's, after that, some dissipation. And for the second case, D equals to 2. And the saturation is different. Yeah. Okay. So we can see again, it's similar to the first one. They rotate, but they do not combine together. Even though both they are like co-rotated, they have the same rotation direction, but they do not combine together. And after that, a little bit dissipation. So we can find here that they never combine together. So why is that? And my explanation for this is, let's just look at the resistance. Okay, so this is the same plot, and I just add the blue part for the resistance. And we can see for the first one, it's the same, and the resistance is on the outside, and they just combine together. But for the second one, we have, because these two vertices have little bit not that close to each other, they have some resistance in the middle. So you can see this resistance is like acting like a barrier between them. So maybe start from here. So it's acting like a barrier to prevent this vortex core from touching each other. So this is the result. And the conclusion. So we can study the Lutec's dynamics based on this matrix governing equations. Because Lutex can be found explicitly through an algebraic equation from the velocity gradient matrix. And the Lutex may not be differentiable at this vortex boundary, but velocity gradient matrix should be differentiable on even analytic, maybe almost everywhere, not everywhere, maybe. And velocity gradient matrix contains not only Lutex, but also its eigenvectors, its eigenvalues. So study this matrix governing equation can also provide us with an insight to other fluid properties. And thank you, everyone.
Thank you.